Hello everyone, my name is Prashant Lakera and today I'm going to talk about a first of a series of a lecture regarding the Linux file system management, in which I'm talking about different file systems we have specifically with ext2 file system or ext3 file system, and what are the major advantage, what are different component, and what are some of the tuning parameters we can use. So, because of the advantage of open source, it offers a many file system. Like till RHEL 6, we have the ext series, and in case of our RHEL 6, the ext4 is the default file system. Or in case of our RHEL 7, we have XFS file system, but you can still use the ext4 file system in a case of our RHEL 6. So, what are the different advantage we have with all these file systems, which we are going to discuss. But before going to discuss about the different kind of file system, let's discuss about an important component called a virtual file system. So basically a virtual file system is a kind of a abstraction layer which lies between your user space process and your file system. So means your file system or your file system implementation. So one of the major advantage which is provided by this virtual file system layer, that it provides a common object model. So means your user process will not need to worry about what to know, or your user process don't need to worry about like which file system is going to use, which system call should be issued for each file system. All these information is being hide or by the underlying user process. So the way the VFS work, it provide a common object model, such as having a common like inode, file object, page cached entry, and whatever the method it is going to access your file system object. So it hide all these difference and act as an important your file system implementation for your user process. So user process will never need to worry about all these things. Whatever the application you are going to write, it never need to worry like what are the underlying file systems you are going to use because of this VFS layer. So it is one of the most important layer which has been provided. And the next part I'm going to discuss is about a journaling. So what is exactly a journaling? Means you can think of journaling as a logbook. So before discussing about a journaling, we have a file system like ext2 versus ext3. So ext3 is the first file system which uses journaling feature. So let's discuss like what are the advantage we have with the journaling with the file system having a journaling. So before that, let's discuss about what we have earlier. Like for example, ext2 is having a file system with having a no journaling capability. So means in the case of a non-journaling file system, whenever any application perform a write, it first update all the metadata and then actual user data next. Okay, so when let's say if your system crashed, so file system check for the inconsistency by checking all these metadata. So this is fine till your data is small or you are not dealing with a big data. But in case your data is big, then it take a lot of time to check this inconsistency, and during this process your system remain inoperational. So this kind of problem been solved by the introduction of this journaling, where you have a where you are going to write the data to the area called journal area before writing it to your actual file system. So means in case of your system or power failure, this journaling area need to be checked rather than checking the whole metadata, and this will solve the problem of your data integrity. So by default, Linux provide three modes of a journaling, in which the ordered mode is the default one. There are two other mode called the general mode or the writeback mode. But the order mode, like for example, when you default your format your file system, the order mode is the default one. So in case of a order mode, means all the data are forced directly out to your main file system prior being committed to prior your metadata is being committed. So let's say your data is first flushed to your file system or to your disk, and then your metadata is committed, which is in a default mode. The second mode, the general mode, which provide you the highest form of data consistency, because it general both your file data as well as metadata. But because it is generating both your file data as well as metadata, it is the highest it has a higher performance overhead as compared to the ordered mode. And the last mode is the writeback mode, which has a means highest performance, but it has it has an issue with the data inconsistency. So let's say your data may be returned into your main file system after its metadata. So first your metadata is returned, and then after your main data is returned. So in the case of a system crash, you will see some kind of an inconsistency between your metadata and your main data. So except for the order mode, if you want to mount any of the file system with any other journaling mode, for example, writeback mode, you will need to provide this parameter data equal to writeback, and then you can mount it. But at the same time, you need to rebuild your init.rd image to make it work. Okay. Now let's discuss about the file system. And like I said, the ext2 is the one without having a no journaling capabilities, and means it is a simple and a fast file system as compared to your ext3, because ext3 has the overhead of the journaling. So like each file system start with a boot sector, and then it divide into different block groups. So your entire file system is divided into different block group, and the advantage of uh, splitting your entire file system to different block group is the performance improvement, uh, because your inode table and your data blocks which hold your user data can reside closer to your disk later, so it will decrease your seek time. So means seek time is what you're like the header need to move to search for your data. So all this will reduce when you're splitting your entire file system into different block group. So block group have a different component, or I can say your block group constitute of different component. So let's discuss about different component. Super block. Super block is one of the most important thing in your file system, and the entire information about your file system is stored inside your super block. So uh, or you can say it record a characteristic of your file system. Means what is the size of your file system, what is the block size, how many blocks are empty and how many are filled, their respective count, what is the location of an inode table, this block map, its user information, and the block group. So this is one of the most important thing, and the exact copy of your super block is being placed on the top of your block group. Second thing, which means with whom your block group is maintained, is something called a block group descriptor, which hold out the information on the block group stored here. Means information regarding your block group stored at the block group descriptor. Then we have something called data block bitmap, which is used for free data block management. Like how many data blocks are free, the information is stored, and that has been taken care by your data block bitmap. Same way, how many how many inodes are free, that has been managed by your inode bitmap. Then after superblock, inode table is one of the most important table you have, which hold all the metadata regarding your file. For example, the access time, the modified time, the change time, and the UID, GID, all these informations are stored in the inode table. And finally, your data blocks. Data block is one of the actually workhorse where your actual data is stored. So like I said, this is how the entire your file system look like, and this is how your kernel used to trace out when it need to trace out any of the files. For example, let's say I run a command called find to find out any particular file. For example, we have like a verilog secure is one of the most frequent file. So means I run a command find. So the first thing the kernel going to do is to parse the file path and search for the directory or entry for your root directory. And means directory entry in the sense which is having all the information regarding like what is holding inside your root directory. Once it's find the directory entry, kernel can find the inode of the next step the kernel is to do is to find the inode of your /var partition. And once it finds out the inode, it again look for the directory entry inside var, like what are different information. And this way it will try to look till it find your file which is been issued by the user, means which is the user want to find out is like verilog secure. So kernel will try to find out the inode, means in this way the kernel will go till find the inode of that particular file. in each and every steps, kernel used to cache all these objects as directory entry cache or inode cache, so that in case of future search, your future search should be fastest. Like the same way, kernel holds out all the cache data. Once the Linux kernel knows that this is the inode of your particular file, then it reached to the actual data blocks, which may be direct mapping or it may be indirect mapping. As the inode of the pointer to a data blocks, as inode has a pointer to this particular data block, by referring to it, kernel can actually reach to that particular data blocks. So this is the way the entire operation works. First, kernel find out the directory entry for your root partition. Then it try to find out the inode. Then it look for the /var partition inode, and then the directory entry till it try to find out the inode of the actual file. Means it try to drill down to find the inode of the actual file, like var secure. And once it find it out, the inode has a direct or indirect mapping to the data block, so it will reach to the actual data. Now, one other thing which I have missed and is like to improve the performance, we can take the general out of the file system and we can place it on a faster media like your smart service disk drive or SSD drive. Because once you take out the general out of your file system, like I mentioned, like how it find out all these entries, so it will reduce the visit count and improve your performance. And like I mentioned, like in each and every step, the kernel will cache all these data, and all these data you can see here in the form of your buffers here. All those entries are stored, and you can find out the more information about it in the lab info where the kernel data structure holds. So here all your buffer, I mean this is what the remote procedure called, but all your actual buffer is stored there, which I'm going to discuss more in the memory section. So let's say I need to create external inode, external general, sorry. So the way I can do is, generally it need to be reside on a separate disk, but for demo purpose I don't have a separate disk, so you can issue this command. Here I'm creating this external general on a partition SDA7. So what I'm telling my file system is to format it with ext4 because I'm using a CentOS 6.2 to create an external general with a block size of this, and this is a partition. So now it's creating a general device for me. Okay, once it has been created, I need to give the actual device as well as the general device. So I created a general device with devsda7. Now I'm getting the actual device. This block size need to be same for both of them. Okay. Now I can check. So in this way I can create an external general. Okay. With the help of, so these are the two commands you need to run. First you need to get a general device, and then you need to format it with this one. The last concept I am going to discuss here is called tune. So what is exactly a tune? So starting from Rails 6, a new daemon which has been introduced, which helps the system administrator to easily and dynamically tune the system depending upon the different workload. So means earlier what we do, like we put all these parameters inside your sysretail.conf, and depending upon your requirement we have tuned it. But now the Red Hat comes out with a solution in which they provide you a different profile depending upon your requirement, and you can utilize it without tuning, means with a little bit of tuning or with a little bit of changes you can use it directly. So say here, these are the like different 9 profiles. So depending upon your requirement, whatever your requirement, you can directly use it. So for example, I'm using an enterprise storage EMC in my background, so I need to tune some of the parameters. Like the same way for Oracle, we need to tune some of the parameters. So you just need to run this command, like adm profile, and choose the profile. For example, I'm choosing the enterprise storage. So it will automatically apply all the settings for you, even change the elevator, and you can even check it here, etc tune hyphen profiles, and for example we change it to enterprise storage. So like change the elevator to, what are the elevator it changed it to deadline, and sysctl. What are the changes it made? For example, change your dirty ratio to 40. This is for the CFQ scheduler. We change all these parameters for you. So this is a little bit introduction about the file system, as well as the introduction about Tune. So thanks for watching this video. In case of any questions or query, you can please write it to me at elierprashant@gmail.com. Thanks for watching.